Hi everyone, this is the solution to example 12 on rotated vessels. So this is the problem. A closed cylindrical tank 450 mm in diameter and 1.2 meters high is filled with benzene of specific gravity 0.877 to a depth of zero point 0.8 meter, causing an initial pressure in the airspace of 40 kilopascals. It is rotated about its vertical axis. Determine the maximum pressure that can develop within the tank for the following cases: angular speed of 180 rpm revolutions per minute, angular speed such that the vortex exactly forms at the bottom center, angular speed of 360 revolutions per minute. Also investigate if a 0.5 mm thick steel can withstand the resulting 0.5 mm thick steel tank can withstand the resulting stress in part 3 if the allowable hoop stress is 16 megapascals. So let's have the figure first. So the radius is half of 0.45 meter, 0.225 meter, the height 1.2 meters high. It is filled with benzene of specific gravity 0.877 to a depth of 0.8 meter. Therefore, the airspace is 0.4 meter, which is subjected to an air pressure of 60 kilopascals. So for the first case, H1 is equal to 0.0005589 omega 180 square radius 0.225 square. So H1 is 0.9167 meter, which is greater than 2 times zero point 0.4. So meaning to say the imaginary parabolic surface of equal pressure of 40 kilopascals will extend crossing the top cover as shown in the figure. So therefore, we need to compute the depth to the bottom center because the maximum pressure occurs anywhere on the intersection between the periphery of the bottom and the walls. So we have a formula for this from my lecture on rotated vessels. Y1 or Y in general equals square root of 2kh. You look at the derivation and I also explained that in my lecture video on rotated vessels. So 2kh where k is 0.4, the depth of the empty depth, and h is 0.9167 or h1. So y1 equals 2 times zero point 0.4 times 0.9167. So y1 is 0.8564 meter. So if y1 is 0.8564 meter, then the distance to the bottom center is 1.2 minus 0.8564, and that would be 0.3436. Therefore, the total depth from here with pressure 40 to bottom is quantity 0.9167 plus 0.3436. So the pressure maximum is 40 plus 0.877 times 9.81 specific weight of benzene times total depth 0.9167 plus 0.3436. So the maximum pressure that can develop within the tank is 50.84 kilopascals. For the second question, angular speed such that the vortex exactly forms in the bottom center. So that's the paraboloid with vortex on the bottom center exactly given by that formula, which I also derived. Capital H squared over 2k, where h is 1.2 and k is 0.4. So 1.2 squared over 2 times 0.4 is 1.8. So it is not calculated here, but if you compute 1.2 squared divided by 2 times zero point 0.4, it gives us 1.8. So that's the value of HV. So substitute maximum pressure which occurs here is equal to 40 plus 0.877 times 9.81 times 1.8. So the maximum pressure is equal to 55.49 kilopascals. For the third angular speed of 360 rpm, so H3 is 0.0005589 times 360 square times 0.225 square. and that is equal to 3.667 meters, which is greater than 1.8 meter HV. So that means the imaginary parabolic surface will extend beyond the bottom, as shown in the figure. And we need to solve this distance. I'll call that y3. This radius r3, and this radius r sub 4. By squared property of parabola, y3 as to r3 square equals y3 plus 1.2 as to r4 square equals 3.667 as to 0.225 square. So r3 square is 0.225 square times y3 over 3.667. R sub 4 square is 0.225 square times quantity y3 plus 1.2 all over 3.667. Then next, let's reinforce final volume of air, which is defined by this parabolic segment with two bases of height 1.2 and radii R3 and R4, equated to the original volume of air, because the final volume of air inside the cylindrical tank is equal to the initial volume of air. The air cannot escape because it is closed. So pi over 2 R3 quantity R3 square plus R4 square times 1.2 equals pi 0.225 square times 0.4, the original volume of air. Cancelling out pi, 1.2 over 2 is 0.6, so quantity R3 square plus R4 square times 0.6 equals 0.225 square times 0.4. Replacing R3 square by 0.225 square y3 over 3.667, R4 square by 0.225 square quantity y3 plus 1.2 over 3.667 times 0.6 equals 0.225 square times 0.4. Cancelling out 0.225 square, then cross multiply 3.667. The left side becomes y3 plus 1.2 equals 3.667 times 0.4 over 0.6. From here, we can solve y3 equals 0.6223 meter. Therefore, the height from the surface of 40 kilopascals pressure down to the periphery of the bottom and the walls intersection is 3.667 minus y3. So therefore, the maximum pressure is 40 plus 0.877 times 9.81 times quantity 3.67 minus 0.6223. The maximum pressure therefore is 66.19 kilopascals. To answer the last question, let's compute the hoop stress, which is given by pressure diameter over 2T, and compare it with 60 megapascals. To be safe, it should be less than 60 megapascals. So the actual hoop stress is equal to pressure, which is 0.06619 megapascals, times diameter 450 mm divided by 2 times 0.5 mm. Mm cancelled. This is megapascal, so the stress is in megapascals. Hoop stress is 29.79 megapascals, which is less than 60 megapascals. That means that this tank can withstand the condition, especially the last condition. So it is safe. So I hope you were able to understand the solution.